All right, so we'll get started. Welcome to the fourth installment of Dive into Deep Learning, the coding sessions. And today we'll be talking about attention mechanisms. So we are also sort of in the middle of our D12 session project. So it's been fun. Let's hope it stays that way and continues. So we'll start with the theory session. I'll be talking about attention mechanisms and what all things we can do with them, and then Kshitij will be leading the coding session. So get started. I'll start with a brief recap of recurrent neural networks. So this was our previous session, and this is what we learned last time, that that recurrent neural networks are sort of like this. They have two inputs. One is an input which could be a word or a character encoded in a specific way, which I'll talk about, and then a hidden state. And what happens is you usually work with sequential data, or places where the ordering of data is important. So you give in some input, it produces a output and a hidden state, and then you give the next input, it updates that hidden state, and so on. So this is what we had learned last time. Also, we talked about tokenization. So neural networks cannot ingest direct words. So what we do is, for example, here we have some strings. He is the king, she's the queen, king is a man, and queen is a woman. And these are 9 unique words which we have labeled from 0 to 8. So now we have converted or mapped our strings or words or characters, and in this case, just words, to particular numbers. And now we can use these for our neural networks. Now, we did another thing which is called one Hotend coding. So if there's a string called he's the king, remember he was 0, is 1, the is 2, and king is 3. So wherever you see is, it's just 1. Wherever you see the, it's just 2, and so on. So now we one hot encode this. Basically, each of the number over here is now converted to a vector of length 9. So this is 1, this was 2, this is 3, and this is 4. So this is what we had learned last time, but there are a couple of things which we didn't talk about and which I'll be talking about now. So the first one is embeddings. So if we read the string over here, which is king minus man plus woman is a queen, this is something which makes sense to us, but this is something which is not being reflected in our one hot encoded vectors as of now. So what we want is, we want our one hot vectors or these vectors to have some more context and some more information about what they are encoding. So what we do is we go with embeddings, and what happens is you take in these fundamental vectors and just add a multi-layer perceptron or a simple network in front of it, and it learns with your recurrent neural networks to see it learns what the dependence between different things are. So here we have 3 French words, and since I do not know French, I won't even try to butcher it. What they have done is, instead of having 1 0 0, there are some numbers which are also represented by intensity here, but since it's not just 1 0 0, these numbers sort of encode what is the relation between one word and the other one. So embeddings, we'll be using them today, is just a way of mapping just these one hot encoded vectors to have some more context in them by changing how this one is sort of distributed throughout. Now, another thing I want to talk about is regarding Rnn training, which is training with teacher forcing or professor forcing. So last time Kshitij talked in detail about how you do backpropagation in time. Now you can do a small trick over here while training your RNNs for faster convergence. So you have some input at time t. You give that input to your RNN, and then it produces a hidden state, and it produces an output over here. And you compare this output with whatever it's supposed to be, or whatever the prediction is supposed to be. And usually what we do is we take this as our input for the next time step. Now with teacher forcing, what you can do is, you need not give it the prediction, you can actually give it the original value with which you were comparing. So this will help the RNNs to converge faster. You can still compute the loss, but the next step doesn't have to start with the answer from the previous step. It can actually start with the correct thing. So this is called teacher forcing, and we'll be again using this today in the coding session. Now, this is what we want to do today. So yes, so in the previous session, we were looking at predicting the next character, or predicting the next word. Today, we are trying to do machine translation. So we have something written in French, and we want to do some deep learning magic on top of it. which will give us an output in English, which is I'm a student. Now this is English, which I know, so I can butcher this one. Okay, so the way it works is you have encoders and decoders. And these are just neural networks which will take in your input, do something to it, and then talk to another neural network called a decoder, and the decoder will give you the output which you're looking for. So the way it works is something like this. So you have your 3 letters in French. They are taken inside the encoder. Encoder produces something called a context. It's just a vector. And then decoder takes in that context and then translates it, uses that context to give you a translation in another language. So this is what I just told you. Encoder takes in all this input, processes it, computes the context and gives it to decoder, and then decoder takes in the context and then does some processing on top of it to give you what you want. Now, the encoder and decoder are recurrent neural networks, and encoder and the context is just a vector. Usually, context is just the last hidden state of your encoder. So we'll look at this in a bit more detail. So we'll start with, okay, so GIFs in Google Slides do weird things that start from anywhere in the middle, but let it run once, and I'm gonna explain from the beginning. So what we have over here is this is the encoder, this is the decoder. This is shown in the unfolded way. So it takes the first word, produces the first hidden state, takes in the second word, produces the second hidden state, takes in the third word, produces the third hidden states, and passes that hidden state to the decoder Rnn, which takes it as its first initial state and then just works on it. So one thing which you should note over here is that first, the encoder takes in the whole sequence, makes a hidden state or a context, and then gives it to decoder, and then decoder starts with that thing and then computes the output which you want. So these two work sort of independently, sequence by sequence. So you'll give encoder the sequence, it will work on it, it will produce a context, and then the context will be given to decoder, and then decoder will start with the context and then produce the output. So that's sequence to sequence models for neural machine translation. Now, the issue with this, if you have not already sort of thought about this or seen it, is that the context vector is a bottleneck. And that's because you're just passing the last hidden state of your encoder Rnn to the decoder Rnn. And this makes it challenging for these encoders and decoders to work with long sentences where you need to see different parts of the sentences, or something which is long, which needs more context. So the solution comes with attention, or the attention mechanisms, which allows your model to focus at the relevant parts of the input sequence as needed. So it was proposed in 2014 and 15 by Wadnow and Luong, and we'll be looking at both of these today. Okay, so before we get into attention in terms of neural machine translation, let's try to do a very simple exercise over here. So here you have the X and Y axis. There's some ground truth, which is given by this orange curve over here. And then you have some observed data corresponding to the ground truth, which is given by all these blue dots over here. And our job is to sort of learn this and or make a prediction at any given X. The very simple thing anyone can do or think of is just take an average, which is given by this green dotted line over here. And clearly this doesn't work very well. You can see it doesn't work very well in this regime, doesn't work very well in this regime as well. Now, intuitively, what you can also do is you can chop this into several segments. You can chop this into a segment between 0 and 1, 1 to 2, 3 to 4, 2 to 3, 3 to 4, and so on, and just take the average of each small segment. So that's like a moving average kind of thing, which you can do, which will do slightly better than what is shown right now. Now, let's add some math to it. Let's add some kernel K, which is just Gaussian, and I'll come to this. And the way we predict is the prediction is f of x, and the way we predict is using this mathematical equation over here. So at any point x is given by this kernel K, which is this Gaussian over here, and you sum over all the points from so this is what this xi is. So suppose you're standing at x is equal to 1 exactly. Okay, so this is x is equal to 1 over here. You'll start with the first point, second point, and so on. You'll go to all the points, put x minus that x value of the point over here, let's say 0, dump it in here, and compute this value. So that gives you for 1x at x is equal to 1, and then you do it for all the values in the bottom, and multiply it by yi. So when you do that for all of the x values, this green curve is what you see is the prediction, which starts to match up your ground truth. And this is how the retool book sort of invokes attention. What they're trying to show is that, so you have this Gaussian kernel over here, and what it does is that it allows you to take in the values which are nearby, say x is equal to 1, which is these values, put a lot more attention or a lot more weight while computing f of x to those values, and the values which are far away, because it's a Gaussian, they'll have very, very small contributions. So this is uh, a sort of a attention mechanism where you're taking a look at all the data, but you are weighing the data according to where you're standing or where you want to predict the value. So this is like a very simple baby introduction to attention, not in terms of neural machine translation. Before we get into that, I want to talk about attention scoring functions. And even before we talk about attention scoring functions, let's talk about Python dictionaries and see what they have to do with it. So most of you will be familiar with Python dictionaries. They have these key value pairs in it. So there's some key which is address and the value which is downtown. And what you can do is you can query a dictionary for a particular key and get the corresponding value for it. So you can say, in my dict, tell me what the age is, and it's going to return 27. And we asking what the age is a query. The key is age, and the value is the pair. So this is what dictionaries or hash maps are. This is how sort of databases work. You try to query a particular thing. It gives you if the keys sort of match up and the value corresponding to that key. But what we'll do now is we'll try to do this in a probabilistic fashion. Now, what that means is that given a query, what's the most similar key available in the dictionary, and just tell me that and give me the corresponding value for that. So that's what attention scoring functions will tell you. And this is what they look like mathematically. So you have some function, which is the attention scoring function for a given query Q. And for all the key value pairs, so this is K1, V1, KM, VM, whatever this key, for all the key value pairs that you have for a given query Q, how we score this. And the way it is done is using a function alpha, which we'll talk about, which takes in your query and your key and just returns some value and returns some number, which you then multiply with the value. So in terms of dictionaries, coming back to dictionaries, what you can think of is if key and query, if the key and the query match exactly, this function over here will return 1. Otherwise, the function will return just 0. So what's going to happen is when key and query match, it gives you 1 exactly and gives you 0 everywhere else. So you only get the value corresponding to that key. But if you want to introduce probability to it, you want to see how close or whatever the closest keys are corresponding to my query. We do that using a set of functions, which we'll talk about next. Since we are talking about probabilities, it's nice to work with numbers which are between 0 and 1. So that's why what we do is we softmax whatever is coming out of it. And softmax is an activation function which you have talked about earlier as well. Okay. So this is what you're trying to do in neural networks. You have a query, you have some keys, you put in your function over here, you get your attention scores, you softmax them, and then you multiply with the values. So let's look into a bit more detail for all this. These are the two equations which I just showed you. So you have a query, you have a key, you have a value, and you just softmax this. So the thing which you have to learn is this a function over here, and you can do it in multiple ways. You can use like a multi-layer perceptron to map your query and your key. So this WQ will be a dense layer or a fully connected layer which maps your Q to something, and then your K, which is your keys to something. Then you add them up, put a tan h, again multiply it with another weight, and so on. So this is called the additive attention. Or you can do something which is very simple. You can just take a scalar dot product between these two and just add some normalization constant in front. So these A functions over here will go inside of softmax. And just because you want to work with probabilities, keep everything between 0 and 1, that's why we have this. So we talked about attention scoring functions, and let's see how we can add attention to our sequence to sequence models, which are encoder and decoder models, and how will attention help us sort of perform better and perform better when it comes, especially when it comes to longer sequences. So again, this has sort of start in the middle, but let's wait for a second. Okay, so here we have our encoder. So we took in the first word, produced a hidden state, took the second word, produced a hidden state, and took the third word, produced a hidden state. And now, in contrast to the normal sequence to sequence model, where you just pass the last hidden state, you pass all of them simultaneously. This is part one of all this. So the encoder part remains the same. You use the same encoder as the normal sequence to sequence model, but the decoder now changes. It's called the attention decoder Rnn, and we'll look into a lot more detail of what an attention decoder Rnn is. So this is like a normal Rnn, but the extra thing it has to take in is not just one hidden state, it has to take in all the hidden states which were produced by the encoder. So let's dive deep into this one. So the first thing which you have is three hidden states, and these three hidden states are corresponding to those three French words which our encoder had produced. Okay, so this is given by H1, H2, and H3. Now, decoder also has a hidden state lying with it, but let's not go there for the moment. So this is what our input is for the decoder, which has all these three hidden states. Okay, and then we use our attention scoring functions, the functions which I just showed you, to put a score to all three of them. So this is 13, this is 9, this is 9. And what this is doing for you is that it's going to tell the decoder network which hidden state is the most important one, or how much to concentrate or how much to pay attention to which hidden state while I'm trying to sort of produce an output. So since this is right after, so this is time step 4, which is right after passing all three French words in our encoder and getting all the three hidden states, you want to put most attention in terms or put most weightage on the first hidden state and not so much on the second and third hidden state. So we already have some attention scoring functions which we use to compute these values. We then softmax them because, again, we want to work with probabilities which are between 0 and 1. And then we multiply these numbers with all of these. So we multiply this with 0.96, 0.02, 0.02, and so on. So that's why you see the intensity sort of dropping, because these are now being weighed down as compared to the first one. We then add all of them and just create one vector. And this vector is now our context vector for the decoder. So in contrast to our sequence to sequence model, where we just had the last encoder hidden state as the contrast, here we are using a linear combination of all the hidden states from the encoder to create a context. Now, moving ahead, again, this started from the middle, so let's let it run once, and then I'm going to tell you what exactly is happening over here. So what we have over here is all the three French words are in. It has given us all three of our hidden states. We take this, we weigh them, we add them, and make a context. And then we take this context and we concat it with the hidden state of the decoder. So now the hidden state of the decoder, which is what a normal Rnn is. So it had some initial hidden state, which is usually zeros. It has the end of sequence, which tells the decoder Rnn that, hey, you need to start now because I'm done processing all the inputs. Okay. So you take these two things, produce a hidden state, concat it with the context vector, and then you put a multi-layer perceptron on top of it and produce I. And then you do the same thing again. You take this I as the input, you use the same hidden state ahead, you create a new hidden state, use the same attention mechanism, create a new context vector. And now you can see it's putting more weightage to the central or the second hidden state over here as compared to the first one. So this is what we do. For each step, we weigh how much, or we apply some sort of weighting to all the hidden states of the encoder. We take that, we make a context vector out of it. We concat this context vector with our hidden state given from the decoder and just put a multi-layer perceptron at the end to get an output. So it's going to give you I, and then it's going to give you M. And then if you continue this, it's going to give you a student at the end. So this is how an attention decoder works. So it's very similar to your normal decoder, except you have this extra part where you weigh all these hidden states from the encoder. Okay, so now I'm just gonna sort of review what we have done and go into a bit more detail of this, and we'll see how this will be implemented in the code. So this is what our normal sequence to sequence model was. You take in some input, it gives you a hidden state. You use that as the second input and the hidden state for the next step, the next hidden state and the input for the next step, and so on. Once your sequence is done, you take in your encoder hidden state, you give it to the decoder Rnn with a start sequence sort of token with it, and then it just goes ahead. So it produces something, you take that as the input for the next step, you keep updating your hidden state. And this is what the normal sequence to sequence model is. Now we have the Luong attention, which is the same sort of animation which I was showing you, but I'm going to just explain it once more. So you have the same encoder part, except the only difference is instead of just passing the last hidden layer or last hidden state, you pass all the hidden states. You take all of these hidden states and create a context vector, and you use this context vector and the hidden state from the decoder Rnn to produce an output. And then this output goes as an input for the next decoder step, and so on. So this is called the Luong attention. And how we compute these context vector is given by those attention scoring functions. You weigh all these states, you sum them up, you put a softmax in front of it, and so on. Okay, so that's Luong attention. There's another kind of attention, which is Bahdanau attention. And there's a very small difference between these two. So the difference is that in Luong attention, you take the context vector, you use that along with the hidden decoder state to produce an output. In this case, you actually just don't do that. You take this context vector and combine it with the input and use that to give you the next output. So Kshitij will be coding the Bahdanau attention today, and we'll go into slightly more detail of this exact of this mechanism. Okay. I'm gonna move ahead and dive a bit more deeper into the Bahdanau attention. So the first step is the encoder Rnn. So that's very simple. You take in Rnn, you give it some input, it gives you a hidden state. You use that hidden state as, and you start with an initial hidden state. You keep updating the hidden state, keep getting new and new inputs, and so on. And this last hidden state, or all of the hidden states, are passed based on whether you're doing a normal sequence to sequence or you're doing attention. In this case, since we are talking about attention, so all of these encoder hidden states will be passed to the decoder. So that's the encoder. This is the simplest part. Okay. The next step is now, how do we compute this attention scoring function? Okay. So what we have is the decoder hidden state, and we apply a multi-layer perceptor on top of it. Okay. And that just gives us this value, which is W decoder into H decoder, which is sort of the part over here. You also have all the encoder inputs with you. You again apply a multi-layer perceptron over here, which is WK, and then you create, or you just map them so that they're in sort of same dimensions and so on. So this is what this and this part is. So your Q and K is the decoder hidden state and all the hidden states coming from the encoder. So this is what you want to do. My query is the decoder hidden state. I want to see, based on my hidden state, how I should weigh all the input encoder hidden states. So that's what we are doing over here. Okay, and this symbol over here is just simply, it just shows a linear layer or a dense layer or a fully connected layer. Okay, and we'll be coding this, and we know how to code this. This is just nn.linear, so it's very simple. This is an activation function which you can always apply, and then we'll work on this one. So now we have two things, which is this one and this one. You add them up. Okay, you sort of add them up, apply tan h on top of it, and then we have the W alignment. So this is coming from basically this part. So you have, in this case, a 1/3 vector over here, a 2/3 vector over here. So what you'll do is you'll add both of them together. So you'll get a 2/3 vector over here. You have this this function over here. You multiply both of them, and it's going to give you alignment scores. And this is what we have A of Q and K over here. So we now apply, so this is the same step just shown, I guess, earlier. And then you apply a softmax on top of it. So this is what the next part is. And then once you have that, you can now use the encoder hidden states and weigh them accordingly and get a final context vector out. And then you take in the context vector, you take in the previous decoder output, concat them and the decoder hidden state, and use that to create a new hidden state, which will give you the final output. So I'm going to go over it one more time, just to make it clear. Okay, so this is what our sort of our workflow is. You start with your encoder. You take all the hidden encoder states, and then you have a hidden state from your decoder. You use that as your key and query pair. You generate some weights, and you use those weights and multiply them, or use those weights to create a context out of all these hidden states. And then you take this context vector and the decoder output, concat it, and the hidden state to produce the next output. This sounds slightly confusing right now, but I think if you have the slides with you while Kshitij is coding, it's going to help you understand. All these figures are also there in the notebooks, so we'll try to sort of go over it again and again so that it stays clear and there's no confusion. So yeah, you have all of your hidden states from your encoder Rnn. You use the decoder hidden state and all the encoder hidden states, multiply them with some weights and add them up, which is going to be shown a slide after this. Sorry for that. And then using this sum over here, you multiply it with some with WT, which is again coming from another layer. You get some alignment scores. You put a softmax. So this was just the 10H part. You apply the softmax. You get the normalized probabilities, and you use that. You use those weights to weigh your input encoder Rnn hidden states to get a context vector, and you use that and the previous output from the decoder to give it as the input to the decoder Rnn with the hidden state, and whatever comes out, you just put a multi-layer perceptron on top of it to get the output. So that's what I have for you today. In case this is some of these things will become a lot more clear once we start implementing them.
So before we actually begin with the coding session, I just wanted to point out that so Ramesh actually shared a really nice notebook using. So he used the Rnn notebook which Devansh coded up in the last session and sort of extended it to add more data set and then make some real nice prediction. So Ramesh, do you want to maybe share your screen and talk about it first?
Sure, happy to show quickly. It's let me share my screen. It's basically the same notebook. You can recognize the function names. In fact, even the contents of the functions are exactly same. What Devansh showed us last time. So I'll just go from bottom up on what it does. So I use this Alice in Wonderland textbook from Gutenberg. So it's basically the entire book. You can take any of these contents. And then you can give a starting key or some sort of a starting sentence, and then it will try to create a hidden state from this, and then using the hidden state basically continue generating new character RNNs, and that basically and continue with the sequence. And here I'm creating a sequence of length 1000, but there's nothing limiting to 1000. You can go 2000, 5000. It just write a whole thing. And what was surprising to me is it's not gibberish, like it may not make complete sense, but it still is like full valid English words, right? Probably it's in the dictionary of the book, these words, but it's surprising that I never gave it the entire dictionary. All I gave it was individual characters to the model, and it's able to learn through that process. And it's a very powerful idea that what's being shared, by Devansh and Kshitij last couple of weeks back, and it certainly helped me learn through by doing. I can walk through this notebook very quickly, and this has already been done a couple of weeks back. The only change I did is I added this thing, which is basically instead of the sample text that Devan shared, I just used a larger text to see how that will behave. That's literally the only change I did. And the rest of it is pretty much the same notebook. You can see that I also removed the punctuations. The first character was some Unicode characters. I removed the first character because it was the only occurrence of the character, so it was not meaningful. I removed that. And then you can see the text here. What was really good is there are 38 characters, 38 unique tokens, which is A to Z and 0 to 9 and a space. Removed all the other punctuations because we remove it. But you can keep it and see, if it will generate better text for you. What I did is actually at every step, I would just print out and visually see what it does. And then, for example, I will print the first 25 text, and then I print the encoded text, and then manually verify that, oh, this is the same. Oh, this is actually P. I could see that that is P and that is R. So it kind of help me understand a little bit what's happening here. And I always never understood this batching into sequences. So this function they gave that I was able to run later on helped me understand how this input sequence is built, how the target sequence, which is just a input sequence offset by one character, you could manually verify it, and that's the advantage of Jupyter Notebook environment as well. And on every step, I will just print out here initially, and then eventually I will make it into functions because I don't want to, I want it to be fully functional, fully usable. So I will manually try individual things, one value at one cell at a time, but then I will convert it into functions, and then I would say, and then I tried with the sample word hello world and verify that this sequence operation is working. And then I created a data set. None of this is mine. It's mostly just taking what they have shared actually, and create a data loader in PyTorch. It's very standard way of creating a data set, which is basically take a text and then convert it, encode it into. In fact, I even pass it the encoded sequence. All it does is just index into the sequence and gives you back the indexed value after one hot encoding, because that's the input for the network for the RNN. And again, I just print it out just to verify it. And then I created the model. Model is nothing big. It's basically a GRU model with linear output with the softmax at the end. And this is also the same notebook. I think they used Rnn. I just changed it to GRU. That's all. That's the only change I did actually. And then what else? I think this is the rest of the training functions are exactly the same. And then I was able to train it for several epochs and get to a really nice loss function here. And then I save the model and download the model because I don't want to run it every single time, so that I can load it later on. And then that's it. And then I just run through the predictions. The only other change I did is I passed the hidden state, and then I would only use the most recent character in my prediction. So instead of passing the whole characters, I would only pass the most recent character and the hidden state. Otherwise, it was running slower in the predictions. That's the only little change I did. But otherwise, yeah, you could try it your own. Give it a try with any other textbook. In fact, I sent it to a friend of mine, Sudarshan, in ML Tokyo. He basically did the same thing with one of the Indian languages, Tamil, and he literally did the exact same thing with tokenization and was generating fully valid Tamil literature, right? That's like, so it's nothing specific to English or any thing. It's anything that can be encoded into characters can be done with this. I was trying to do this with music, but I never got to the end of it because there's some converting the wave file to MIDI file, and I got stuck in those process. But that'll be interesting to see if anybody can try out other literatures as well. And yeah, just I shared it on the ML Tokyo Slack. I will share it here as well if people are interested. I just only shared it. Yeah. And yeah, I just want to say that these notebooks that they share are very functional, and I'm looking forward to trying something with today's version of notebook as well, and expand my own understanding of it. And hopefully you can do it as well. It would be nice to see other people take the notebooks that's shared and move forward with it. Yeah. So thank you guys. Thank you. It's all your efforts that I was able to extend a little bit.
Thanks for sharing, Ramesh.
Yeah, this is really, really great. And I would, like he said, I would encourage everyone to just copy these notebooks over and try it out. And we are trying to make these notebooks as sort of generic as possible. So you can just switch a data set or make a few small changes in the functions and then just run it on different kinds of things. And that's sort of the aim with today's notebook as well. So I think we can, let me just start sharing. Okay, so can you confirm if you're seeing the live notebook?
Yep.
Okay, yeah. So, yeah, so let's begin with the coding part. I'll just brief about what we are going to do in the coding part first. So we are going to go basically write an encoder decoder network from scratch. Everything starting from data downloading, data preprocessing, generating of a vocabulary, writing the encoder, writing the decoder, combining them into a sequence-to-sequence model using the using the encoder and the decoder, then writing the training loop to basically train it, and then writing an evaluation loop to basically show what predictions it's making. After that, I'll show you how, by only making very small changes to these two classes of encoder and decoder, we can just make it, we can make that attention network which Devansh was discussing. So that's why we are going to spend a lot of time on the encoder decoder part, which would not have the attention, but just changing a few lines in those encoder decoder. In fact, just changing a few lines in the decoder network would give you the attention, and then just changing a few lines in the way we combine those two classes is all you need to do for the attention mechanisms which Devansh was discussing today. So yeah, let's begin. So just quickly. So I'm using because we are going to do training and everything today as well as we go along, I'm using the GPU resource. So just to make sure it all runs. And then, okay, so this is just importing. Oh, what happened? Okay. Well, let's wait for it to connect. So yeah, these are just, yeah.
Do you have another notebook running?
I don't think so. I think it connected now.
It's probably connected to CPU, I think.
Is it?
Yeah, check. Yeah. I think you have another notebook which is running somewhere.
Check. No, it's connected to GPU. I think it's running now.
Okay, fine.
Oh, wait, okay. So let me try to, I don't think I have another notebook running.
I think now you connect without GPU. If you go back to the runtime again.
Okay. So if I just do GPU.
Oh, it is GPU. Oh, it is GPU. Okay, that's perfect. Thank you.
So runtime, restart runtime. Let's see what happens. It was working a few minutes ago.
I think it's working. You can try NVIDIA somewhere to confirm.
Oh, okay, so it's running now. All right. So now it's running. So yeah, these are just the encoder decoder representations which Devansh also showed. Just to remind you. So the idea is that we give a whole sequence as an input, and EOS or our token, special token, tells us what the end of the sequence is. So the encoder knows that this is the end of the statement. And once all that is done, we get the hidden state out of the, or the context, we get the hidden state out of the encoder. That hidden state is passed into the decoder as its own hidden state. And we give another token as the input, which is the beginning of the sequence. And then the decoder just starts giving us the outputs of the words. The second one, this third one, which I'm showing, which is passing all the three hidden states, is actually what we do for the attention, wherein we are not only passing the final hidden state of the encoder, we are passing all the hidden states of the encoder to the decoder network. But let's just begin with the encoder, just the simple encoder decoder part, all right? So, okay, so we'll start with downloading the data. And then there is this really nice website which actually shows, you can use to download these bilingual sentence pairs of for many different languages. So these are just zip files and you can download them and uncompress them. I am doing it for French and English. So All right, so it's downloaded and that's it. It will make a temporary directory in your Google Drive and then save it there so we can access it. And these basically just contains pairs of sentences and pairs of words for both languages. So before we start even generating our model or writing the model architecture, we need to do two things. One is we want to prepare our vocabulary. So we want to read in all those sentences which we have just downloaded in both languages and make like an indexing. So you might remember like Devansh did the int to character or character to int, wherein each character was mapped to a unique index. In this case, we are not doing a character level RNN, we are doing a word level RNN and actually a sentence level RNN. So we are going to map individual word to individual indexes. So that's what I'm sort of doing for the in this class. So this is the language class. We will make two language classes, one for the source language, the other one is for the target language. So source language is English, the target language here is French. We'll do that for both the languages. The class is initiated with just these empty dictionaries, wherein this dictionary would map a word to an index. The other dictionary will map that word to the frequency of that word. So for example, how many times a particular word occurred in our whole data set. Then this is mapping the index to the word. So, and we are initiating it with the start of the sentence and end of the sentence. So these are given index 0 and 1 by default. And then number of words, because we have 2 here, we'll just say 2. Then we have these two helper functions, one which adds the sentence and one which adds the word. So the sentence is basically, you give it a sentence, it splits the sentence based on the space, finds all the words and add them using the add word function. Add words, what it does is it sees whether the word is present in my dictionary. If the word is present in the dictionary, then it just increases the word count. So basically only the frequency is increased. But if the word is not present in the dictionary, then it adds that word in word to index, it assigns it an index and just says that the value of n words, so the total number of words increases and then the count of that word is set to 1. So this is just a helper class which we'll use to manage all the words, manage and get all the indexes from different words we are going to see from these two languages today. So let me run this. And then here I'm just defined the max length to 5 and we will use it. So we are just going to use the sequences which are of length 5 at max. But there are sequences which are much, much longer in this bilingual sentence pairs. The next part is preprocessing. So again, we want, like Ramesh also mentioned and Devansh also did in his 2 weeks ago, we want to remove some of the unnecessary characters. So this function is going to do that. It's basically going to remove anything which is not within uppercase A to Z and lowercase a to C. So it's going to remove anything which is not alphabet. And then we are just going to apply some normalizations to the data to basically standardize it, remove unnecessary characters, encode it properly. So what we are doing is okay, let me just write this main thing and then I'll explain what each of the individual part is doing. So, all right. So yeah, I'll start with reading the file. So, and I'll read the file using this function read file. And then this file is just going to be my file name, then language 1, language 2. So these are just going to be the strings which give me what the indexes of the language values are. Then I can even print what language I read. So read this sentences, sentence pairs, and then I can tell it what the how many sentences I read, and that would basically be given by this data frame which I just made. So this is going to just read that file, which I'll give it as input in a data frame, and then I'm just saying how many sentence pairs do I have. And then I'll say that I have a first sentence, and then I'll have a second sentence, and that will be done by read sentence. So read sentence is going to basically give me individual sentences using the whole data frame. So this data frame is the input, lang1 and lang2. So these will be the names of the languages I want from that data frame. This is the data frame of the pairs. And then this function will just give me those two individual sentences out for those two languages. Now we'll do the interesting part, which is we'll use the language class which we made earlier and make the objects, the source object and the target object of those language classes. So I'll just initiate that class. So this is just initiating the class, and now we'll populate this class with values. We also want to keep a track of all the pairs, which we will use for training. So this. So now I will loop over this whole data frame. So each row of the data frame consists of, actually, let me just quickly show you the data frame first. I think that would be better. So if I do read file, and then I think this, so this fra.txt is the file I downloaded. My first language name is English, and the second language name is French. Oh, I have to run this first. So let me remove this, run this. So yeah, let's see what this read file does. Okay, so it read the thing, and then yeah. So this this data frame which we just read contains these pairs. So this first column is English words and English sentences. The second column is the French words and the French sentences. So what we are going to do here is just extract the individual words, make our whole vocabulary out of it, extract individual sentences, and then just save these pairs as well, because all of this is what we are going to need for our training. So yeah, so we'll loop over all this, all the rows of the data frame. Then we'll say a length of sentence 1, because we have already read those sentences. So this read sentence has already given me all the sentences. I dot split, and I have a maximum length of the sentence, right? So I want to make sure that I only consider the sentences which are less than my maximum length. So max length, and I want to do the same thing for sentence 2. So I will only consider the sentences which are whose length is less than my maximum length. Then I will say that I will define this array. So this is just a pairing, which will contain sentence 1 and then sentence 2. So this is my pairing, which I'll append in this pairs array, pairs list, and then source.add sentence. Sentence 1. This is just adding that particular sentence in the language class or language class object. Same for sentence 2, because sentence 2 is the target class and sentence 1 is the original class, a source class. And then simply pairs.append full. So, and then we'll just return source or target and pairs. So let's see if this runs.
I think there's a typo on the line. If length equal to that length only parenthesis needs to end at split. It's not after the end maximum. Yeah. Length,
yeah. Okay, so this, yeah, sorry, thanks. Yeah, so the length is to be compared with the maximum length. Yeah, thanks for pointing it out. So yeah, so I read it, and then this is just the file which we read. Now we can actually read the whole data set and then process it and make those two classes. So let's just define the names so that in a variable so that we can easily call it. So our source language is English, the target language is French. My file name is fra.txt. Now I can call source target and pairs is process data. and then it takes file, it takes language 1, it takes language 2. So these are the inputs which it uses. And then I can, so let's do this afterwards. Let's see what this does. Let's see what I did wrong. Sentence one is this, read sentence. Process data, attribute.
I think read sentence is not returning a list. I think read sentence is a string. It is returning a series.
Should work as is. Let me see if, let me just compare it with my thing and make sure it's working right.
Yeah, it's returning a series, so you can print what read sentence is returning. I think you have to add like a index 0 or something in front of it. But yeah, try using read sentence with your, you have already loaded the DF.
Yeah.
Try it with like.
Oh yeah, so it's returning this thing. So if I just do this, oops, then it would give me the list. Okay.
Yep.
So I can just do. Let's try it again. Wait, I think I'm doing something else wrong. One sentence, one dot split, less than max length.
I think instead of list, if you just say sentence one dot values, you will get NumPy array, and then I think you can index into it instead of that list of sentence one. If you just say sentence one equal sentence one dot values. No, it's not a function. I think just
oh, okay. Just values. Okay.
Values. I think that's all it is. And don't use a list. Yeah.
Let's see. Trying to make sure there's nothing that's correct. And then there's df sentence one dot split. Oh, I see. This is what I was doing incorrectly. It was I was giving it the whole array, but I was supposed to give it.
Okay.
That was what was incorrect. So because I have to do it, it needs sentence by sentence, and then I just wanted to give it individual sentences instead of the whole array. So that was what was incorrect. Now it should work. Yep. Yeah. So now we can just randomly sample one of the sentence and then just see one sentence. So let's just random dot choice and then pairs. So that will give us one value, and then okay. So this is what rand. So yeah. So basically, this pair is just a list of pairs. So in English value, and then French, and then you can try it a bunch of times, and it'll keep on randomly giving me values. So pairs is just a list of pairs, English to French or French to English, whichever way we want to go. We can also print the number of words which are there in our data. So the source contains this. So these are the number of English words we have. unique English words we have, and then these are the number of unique French words we have in our data. Then we can also print some pairs. Let's just sorry, 5 values. So these are the top 5 pairs. Just go and then hi, and then we can also see the longer ones, which were towards the end. So congratulations on your anniversary, and then the French translation, and then just pairs. So just wanted to show that the pairs are also of different lengths. It's not just a single length sentences. These are long sentences based on what our maximum length was. So all of them are smaller than our maximum length. And then just to show you that these source and target themselves have classes which have index towards map. Let me just show you some index word combinations. So I'll just quickly define some IDs, just some random numbers. And then I'll just print for IDs source dot. I want index to word, and then I'll just have to use the index. So yeah, so if I also print the ID, so yeah, so 0 index corresponds to the start of sentence, and then this index corresponds to a word, and so these index individually corresponds to some particular words. We can do the same thing for target. So again, some indexes correspond to some words, and it works the other way around as well. If I just use target dot word to index, and I give it some French word. So target is French, and then source is English. Oh, sorry, it's a dictionary, so I have to be careful. Yeah, so it will, so given a word, it will give me the index, or if I have an index, I can find the word. So that's the whole idea, and all of those things are saved inside these 2 objects of our language class. All right, but this only gives us indexes. What we eventually want are tensors. So I have these 3 functions which helps me do that for all the sentences. So this is index from sentences. So I give it a language and the sentence. It splits the sentence, gets the word, and then gives me the indexes of those word. This will make a tensor from sentence again. So it will give, you will give it a language class object and a sentence as input. It will make the indexes. It will append the end of statement, because we need to append the end of statement so that it knows that the sentence has ended. And then it just converts it into a torch tensor and returns a torch tensor. And then this just does it for the whole pair thing. So I simply have to call input tensor and then output tensor. And then I just have to call this tensor from sentence and give it all the sentences. So I'll give it input language and then pair and pair 0. And then again, the same thing. So pair 0 would give me all the statements of the input language or the source language, and then pair 1 will give me all the statements of the target language, and then this will just give me the tensors, and then I can return it input tensor, and then I can return it as a tuple. All right. So let's just pick a
output tensor should map with the output language.
Oh yeah. So yeah. So let's just use a random pair, random sentence. So let's see. So yeah. So this is an English sentence I chose. Just and then what I can do is I can see what the indexes of this sentence are. So each of the word like I'll and pack would have a corresponding index, which we can get from word to index. So I think I showed this earlier, so let's just not dive too deep into that again. But what I wanted to show was that this tensor from sentence or tensor from pair will actually give me the sentences. So if I give it the input language, which is the source, the output language is the target, and then a particular pair which I'm interested in, which is this particular pair, then it will give me it will return the tensor of that particular pair. So if I just print that pair, that pair had 2 words in the English and 3 and 4 words actually in the French translation. So the tensor had 2 particular indexes and then the end of statement index, and then 4 indexes in the French and then the end of statement index. So we append the end of statement to every statement or every input we have. So this TensorForm pair will just give me the tensor value, and these are the tensor values which we'll actually end up training over. Okay, so this basically concludes our pre-processing part. Now we can start making our encoder network. So yeah, so this would be very similar to the RNNs, Rnn which Devansh coded up in the last session. So we'll firstly init this class. We'll have a super, which basically is the way we do things. And then we define the input dimensions. We define an embedding layer, which does the embedding. Then we'll have a GRU layer, which is the RNN layer. And then we'll write the forward function. So let's begin. Define init. And then it needs all the inputs. So we will have an input dimension input. We will have a hidden dimension input. We'll have embedding dimension input. And I think that's it. So this is the init part. Then we'll do the super encoder. The name of this, these 2 names should match, otherwise it will give an error. Self.init. All right. Then we can start defining these different dimensions. So self.input dimension is input dimension. Self.hidden dimension is hidden dimension. Self.embedding dimension is embedding dimension. And then we'll also add another thing, which is self.hidden layers. And I think that is another input I forgot, which is the number of hidden layers. So layers. So this will be the number of layers. Let's just call this number of layers as well. Yep. So now we have defined all these different dimensions. Now we can start with initiating the embedding. So self.embedding is nn.embedding. And then the input to the embedding would be the input dimension, which is because inputs are directly passed into the embedding. So this input dimension is the input to the embedding. And then the output would be just the output of the output would be the size which we specified as the embedding dimension. Then we can make our GRU, which is the RNN which we are using. You could use a simple RNN. You could use an LSTM. It doesn't. It just has to be an RNN because encoder is an RNN. Decoder itself is an individual RNN. So here we are just using a GRU. GRU. And then the inputs to the GRU would be, so we have input, which is passed inside the embedding layer. Then that gives us the embedding dimension. So that will be the input dimension of the GRU. And then we have to specify what the hidden dimension is, and we have to specify what the number of hidden layers are. So that would be the self.hidden dimension, and then number of layers is just number of layers. So this will give us the GRU. Now we can write our forward loop. So forward loop will basically have, so the input will come inside the embedding will give us an output will be passed to GRU, that will give us an output and a hidden, and then the output and the hidden will just be returned. So we will have an embedded layer, which is going to use self.embedding. The input to that will be just the input, and then we will reshape it so that its size is correct. So this is just reshaping. then this embedded layer will pass inside the GRU layer. So self.gru. And then the GRU will also take the previous hidden layer, right? Because it's an RNN. RNN takes two input. One is the normal input and another one is the hidden layer at the previous time step. So it will take this hidden layer and the output of the embedding. And it will also give us two outputs. One is the output and other is just the hidden. So these are the two outputs. And then we can just simply return those two things, output and hidden. But another thing is when we initialize this encoder, we need to initialize the hidden state because initially it needs some initial hidden state. So that's why we will write another function through which we can initialize some values to the hidden states. And that's how that's the first hidden state which will be passed in the encoder. After that, it will start calculating the hidden state. So it's just able to manage everything. So we'll make this function init hidden. It does not need anything. And we will just initialize it with zeros. And then the size of this would be dot number of layers 1 and then self dot hidden dimension. So this is just a 0. So we'll just initialize the hidden state of the encoder with zeros. So this is our simple encoder, simple RNN like we did in the previous session. Oh, yeah. The indenting is weird. I don't know why the indenting is a little bit weird, but okay. So that was our encoder. Now we'll move on to the decoder. We'll follow similar things. So we'll init it. We'll do the super. We'll define the input dimensions. We'll define a GRU. But the decoder will have a few extra things, as we'll see. So again, initialize it. It will, instead of taking the output dimension, it will take input dimension. It will take the output dimension. So this is the, because decoder will get the input from the encoder, right? So this dimension is basically coming in from the encoder. Then it will have a hidden layer, so it will have hidden dimension. It will have an embedding layer, so it will have embedding dimension, and then just the number of layers in the RNN which we'll use in the decoder. So here, instead of encoder, this will be decoder. Now we can start to set all of these different parameters which we defined. I think you can just quickly copy paste these, save time. Instead of input dimension, this has to be output dimension. Hidden dimension same, embedding dimension, and number of layers. Yeah, so that's basically all we need to define. Then we will define the GRU, which we are going to use in the decoder. So first step again would be embedding. So it will use the output of and then embed it into the into the embedding dimension. That will be passed to the RNN, and that will be passed to a linear, like the multilayer perceptron, which Devansh was saying. So after the decoder, we have a multilayer perceptron, which gets which will basically give the output. So let's just add those layers. This is going to be the same thing. Instead of input dimension, it will take the output dimension. Then we will define our RNN. So self.gru is nn.gru. Again, the inputs would be basically the same. It will take the embedding dimension. It will have the hidden dimension and the number of layers. So let's just use this. So this, yeah. So the embedding dimension is the output of the previous layer. So that will go inside this. Hidden dimension is just the number, just the hidden dimension, and then the number of layers basically which we want to output. Then, as I said, we will have a linear or a multilayer perceptron layer which will give us the output. So let's just define that, nn.linear, and then the linear will the size of this linear is going to be starting from because it's going to take number of the hidden dimension as the input, and then our output could be this output dimension. So this is the output which we are going to give from this. We will also define an activation, a softmax, because we need, like Devansh was saying, we are working on probability, so we'll just define a softmax, and we will use log softmax in this case. Dimension is -1. Oh, sorry, 1. Okay, so now we just need to write the forward loop for the decoder, and then we can start combining the decoder and encoder in our sequence to sequence. So the input would be input dot reshaping that input into this size. So this is just 1 comma the batch size. So just -1 will take the whole remaining axes. We'll start with the embedded. So it will take self.embedding, and input will go inside the self.embedding. And we will also apply a ReLU activation function on this. This embedded will then be passed inside the GRU. So self.gru. But then Rnns also take the hidden layer. So this hidden and the embedded both are being passed into the GRU. This will give me, let's say, oh yeah, this will give me output and then the hidden, because that's what Rnns return. Then this output will be passed inside our out layer, which is the linear layer I defined here. And then we'll apply a softmax on it, and that's what is going to be returned. So let's just call it prediction. That is going to be, so we'll say self.out. It will take in the output. And then we will apply self.softmax. So yeah, so we gave the output to the final layer. We applied the softmax activation on that, and then that's the prediction. And then now we'll just return the prediction and the hidden state. So this is going to be our decoder. Again, it is not happy with the indentation, probably. Is it not happy? Okay. So yeah, any questions so far? We are going to now just combine these two classes into a single class, in a sequence to sequence class, and then write the training loop and then train this. So, but any questions so far?
Nothing on the chat as of now. There's an old question, which is, can you please back to the previous cell? But that came like 25 minutes ago. So it's solved. Okay, thanks. Yeah, I think you can go ahead.
Okay. So yeah, so now we'll have this third class, which is our final model, which we're going to use, the sequence to sequence, wherein we'll give encoder and decoder as the input, and this CUDA device, which we are going to use. Again, this is the same thing. Now we'll initialize the encoder and the decoder. So it will be self.encoder. Self.decoder. And we will do another thing. We will initialize the, so when we initialize the encoder, we also need to initialize its hidden layer. So we'll just initialize the encoder hidden layer here as when we are initializing this model once. And then that hidden layer can just be passed on. So we'll just save that. Encoder hidden is self.encoder dot init hidden. I think that's what was called, and then we'll have to pass it to the CUDA device. So we are just initializing the the first hidden layer of the encoder. All right. So now we can write the forward loop for this thing.
Hidden state, right?
What?
Hidden state. You're initializing the hidden state, not the layer.
Oh, sorry. Yeah, sorry. Yeah, hidden state. Yep. Yeah, we are initializing the hidden state. So yeah, now we can write the forward loop. The forward loop will basically have the two language objects which we made, right? So using that language class which we had, so this forward loop will have the source and the target. And then let's see what all things we let's just start writing the forward loop. So we'll take the input length, basically number of words in the sentences. So actually, yeah, it won't have the language classes. These are just the sentences we are giving it as input. So input length. Input length is just the source dot size, I think. Then we will define a few other things. Batch size is how many sentences are we passing simultaneously, so size 1. Then we will have a target length, which is just defined from the target. So target dot shape 0 in the length of this. Oh wait, shape 0 would give me the length. Yeah. So this is going to be, so because we are mapping from one language to the other, the source length and the target length could be different. So this is just the target length, and then we are going to loop over it eventually. Then we can initialize a variable to hold the predicted outputs. So outputs would be equal to, so this will just be torch.zeros, just defining zeros here. And then what are the inputs to this? This will have target length along with the batch size and the vocabulary size as the input. So size, and then we'll have to send it to device, and then we will define vocabulary size as well. So the vocab size will be basically self.decoder.output dimension. So what happens is the output of the decoder would actually be probability for each word in our vocabulary. So given a particular word as the input, the output of the decoder, so the decoder will tell me what the probability of each word in its whole vocabulary is. So that's why this vocab size is needed, and this output dimension is across the whole set of vocabulary we have. And then using the probabilities, we can figure out which probability is highest, and that is basically our prediction word. That's the idea. So that's why this output has these dimensions. So the target length, which is the length of the sentence, which is the number of words in that sentence. What is the batch size, and then vocabulary, because for each case we will have that dimension. Now what we will do is we will encode every word in a sentence. So as you might remember from Devansh's presentation, you pass on all the inputs to the encoder, encode everything, and then the decoder, then the decoding process starts. So we will do this first step where we are encoding all the inputs. So we'll start with the encoder hidden layer, which is my self.encoder hidden. So this is my initialized encoder hidden, and now we are going to keep on updating it, right? So for I in range, my input, because I have to loop over the input length. So I will loop over each word in the input. So this is my a for loop to loop over all the words. And then I will apply encoder on this. So encoder is just literally self.encoder because we have saved it. That would be input. Yeah, so that would be our, oh yeah, sorry. It would be our source at ith index, then encoder hidden. So these are the two inputs the Rnn will take, the input value and then the encoder hidden value, and it will return encoder output along with the new hidden state of the encoder, and then that will just keep on, that will again go back to this as we are looping over all the words in our sentence, looping over all the words in our input sentence. So then we will pass the output of the encoder or the final hidden state of the hidden layer of the encoder as the initial hidden layer of the decoder. So, oops. So I can just say decoder hidden or decoder input as, so this encoder hidden layer will just be passed Wait, sorry, I'm doing something wrong. This does not make sense. Decoder input, yeah. So encoder hidden layer will be passed as the decoder hidden layer, but the initial decoder input would actually be the start of the statement token. So SOS token. So sorry for that confusion. The input of the decoder hidden, the first decoder hidden layer will be the encoder hidden, but this decoder input is the first input, and that will be just the start of the statement token. So tensor, and then we have already defined our SOS token. So we'll just use that. We'll send it to device as well. Device equals device. Yeah. So this is just our start of the statement token. That is the first input of the decoder. Yeah. And we have to pass we have to define the decoder hidden layer. Decoder hidden. And that is going to be our encoder hidden layer passed to the device, like I was doing and got confused. So yeah, so the final encoder layer, after all the inputs have been passed, is going to be passed to the decoder as its first hidden layer. And the first decoder input would be the start of the sentence token. So that's what we are doing here. This comment is for this statement. So just, yeah. Okay. Now what I can do is I can loop over the whole target sequence and ask the decoder to give me predictions. So for t in range target length, yeah. So I'm going to loop over the whole target, and then that will give me decoder outputs. So decoder will give me two output, decoder output and decoder hidden. So will be by self dot decoder. And then the decoder will take two inputs. One is the decoder input, another is the decoder hidden, like any Rnn does. So an input and a hidden layer will give me an output and a new hidden layer. And then as we loop over this whole thing, this will just give me a decoder output. But then Devansh also talked about the teacher forcing method, wherein you don't have to necessarily give the output of the decoder as the next input of the next time step at the decoder. You can give it the actual the source values, the real ground truth values as the input to the next at the different time steps. So we will actually do that as well here. So what we will do is we'll define another input, which is going to be a teacher forcing ratio. So what percentages of time do we want to give it the actual input? What percentages of the time we want the previous decoder output to be fed in as the input of the next time step? So we'll just say that this forcing ratio is 0.5. So half of the times we're going to give it the correct input, half of the time we'll let the decoder output pass on as the input to the next time step. Outputs time t would be, we'll just save that in the decoder output because we want the outputs. So we made this variable to hold the predicted outputs, and we want all the outputs at different time steps. So we are going to save the decoder output at step number t in this array. Then we can apply the teacher forcing process, and then just because we want to do it 50% of the times, we'll just say random.random. That will give me a number. If that number is less than whatever my ratio is, then it will be applied. Otherwise, it won't be applied. And then, but then, as I said, our output actually contains the probabilities for all the different words. And we want to do it, we want to see, we want to find the word which is most probable to be passed. So I will use this decoder output, and I will do this top k, and this will just give me the top k value over a list. So the decoder output has probabilities, and I just want the most probable value and the most probable index. So this will be the most probable value and the value, and then the most probable index of that value. I think I is better. So yeah, so the decoder output will have probabilities for all the words in the vocabulary. I'm getting the most probable value, and then. But then in some cases, I would want to pass in the actual input. So I'll just use my target sequence and get the correct input, which is to be passed. So that will be, if my teacher force thing is true, then you use target at an index of t. But if my teacher force is not true, then I will use the stop I index, and that's it. So in 50% of the cases, the teacher force will be true. Then it will use the actual input, which was supposed to be. While in the other cases, it won't be true. Then whatever the decoder gave as an output will be passed as the input to the next time step for the decoder. Yeah. And then we have another final change. I think this should be decoder input because it's looping. Yeah, otherwise it will always take the SOS token as the input. Yeah, so this should be decoder input actually. Yep. So yeah, so teacher force. So if we do not, if we are not doing this, if we are not applying all this, or if our input dot item is decoder input dot item is the end of statement token, then we'll just break. Because if we encounter the end of statement token, then we also want to break. So yeah, we'll run this. All right, no weird issues. So now we have all the things which we wanted. Here I have just some default sizes. So embedding size, hidden size, number of layers, number of iterations. And then we can now initiate our encoder, decoder, and sequence to sequence models, and then see what is happening. So encoder is encoder, input size, and then hidden size, and then I think it needed embedding size, embed size, what else? Number of layers is equal to number, yeah. And then the decoder also took the same input, so decoder, so input size, hidden size, but it actually needed output size as decoder needed the output size. So this is output size, hidden size, embedded size, and the number of layers. And then our model would be this sequence to sequence, which will use encoder, decoder, and then the device. So encoder, decoder, device, and then we will send this to the device as well. Input size is not defined. Did I not define it earlier? I thought I defined it earlier. Let me check. Yeah, so the sizes would be, like I was earlier saying, would just be the number of words in the source and then the number of words in the target. So these would be the sizes. Now it should just work. Yep. So now we have the model. How much time do we have? I think I've spent a lot of minutes. How much? 15 minutes?
20 minutes. Yeah.
Okay. I think we don't have time to go through all the things I was planning to do. So I was going to write a whole training loop for, so firstly going to write a training step. So defining the optimizer, going through all the iterations, looping over that. Then using this model to do the training. Then I was going to run the training itself. So write the training loop, run the training, let it run for a bit, see the predictions of the training, and then write an evaluation loop to do a bunch of predictions over a lot of different statements randomly drawn from our data set, and then evaluate those randomly. But given that we only have 15-20 minutes, let me just very quickly skip this. I will share the notebook, which will have all these code in there, so you can try it out and run it. But let me just quickly talk about this Bhardnau attention and how it is very slightly different from the one which we have seen. So yeah, like Devansh mentioned, this Bhardnau attention has the attention mechanism in it, wherein all the encoder hidden states are used. and the attention mechanism is used to form the context vector, which is then combined with either the output, either the input or the decoded hidden state to get to the next time step. So this is our encoder network. The encoder network for this Bhartnow attention is also exactly the same as what we wrote. So we will not even write it. We will just use the one which we wrote earlier. The only difference in the decoder is that we are calculating these alignment scores. So we have the hidden state of the decoder, we have the hidden states of the encoder, we apply a fully connected layer, we calculate the scores, apply a softmax on it to get the attention weights. And this is being represented here as well. Then once we have the attention weights, we multiply them with the encoder outputs to get a context vector. We concatenate the context vector with the previous decoded output, and then pass it on inside the Decoder Lstm along with the decoded hidden layer. So the Decoder Lstm, so there are basically just three things we need to consider in the decoder. Any Rnn can take in two inputs, right? One is the normal input, other is the hidden state. So we have a decoder hidden state, and we have the input of the previous decoder step, right? The third thing which we have here is the context vector. Now we have these three things, and encoder takes in two inputs. So you can either combine context vector with the previous decoded output and give it as the input to the decoder, or you can combine, some people even combine context vector with the hidden state and then give it as an input. So there are multiple ways in which this can be done. Here we are concatenating the context vector with the previous decoded input and combining it, and just the decoder hidden layer will be just passed in as the input. That gives us the new decoder hidden layer. We apply a classification layer on top of it, or just a multi-layer perceptron, a single layer on top of it, and that gives us the output. So the decoder itself would not be very, very different. So let's just copy the decoder I made earlier. And just make small changes in this to make it to modify it to the decoder which we want. So I just call it I don't know, decoder. All these inputs are going to remain the same. This is exactly the same. These things are going to be the same. There's no difference. Embedding layer will be there. We have a GRU layer, but the difference is before we reach the GRU stage, before we reach the input, the decoder LSTM or GRU stage, we apply all these alignment functions, and then we calculate the attention weights. So that to do that, we'll need to define a fully connected layer. So we'll have a fully connected layer hidden, and then we'll have another fully connected layer which will be used for the encoder. So because there is a fully connected layer after the hidden, and then there's a fully connected layer after the encoder. So we'll have these two fully connected layers. So these will be basically this W decoder and then W encoder. And then we have another weight matrix, or another fully connected layer at this W combined. This we will just do using self.weight and then .parameter. Using this, we can just give it another layer. So torch dot so tensor 1, hidden dimension. And then these two layers will just have hidden dimensions as input. So just to do it quickly, I'll copy paste things. So yeah, so it will take in the hidden dimension as input. So you got the output dimension in the embedding, that gives us the embedding dimension. Then you have hidden dimension and in the hidden layer, and it's mapping to the hidden dimension itself. So the sizes are just same in these two cases. This is the weight, which is a 1, hidden dimension. Then we'll pass on the GRU, but now it does not take in the embedding dimension input. It will take the hidden dimension as input, input size. But actually it will take hidden dimension times 2. So sorry. So the input to the GRU, because we are concatenating two vectors of length hidden dimension, will be twice the length of the hidden dimension because we concatenated two vectors. We were still saying that it will have the other parameters just remain same. This is also going to remain same. There is nothing changed in this. Log softmax is still going to remain log softmax, but we will need the normal softmax as well. So we'll just define two things, softmax, and then, so now we will have softmax and log softmax. And then in the forward, some of the things are going to change. So we will we will use this log softmax and softmax both in the forward. So let me again to do it quickly, just copy paste the things and then show you what's happening. So it's, if you compare it to the original code, then it's not very different. We have the encoder now the inputs would be an input, a hidden layer. But the special thing here is that because we had the attention mechanism, we need all the encoder outputs as the input. So we are going to use all the encoder outputs. We have the input layer. We embed the input layer into the embedding layer. Then we use the hidden layer and the encoded outputs. We apply the fully connected on top of it. We add them. We apply the tanh. We do the batch matrix multiplication with the final weight layer. So this is this step. So fully connected on the hidden layers. Then you apply the batch multiplication with the another weight layer. That gives you the alignment scores. So this is the alignment score. You apply the softmax on the alignment scores to get the alignment weight, or to get the attention weights. Then you multiply the attention weights with the encoder outputs. So all the encoder outputs multiply to the attention weight, and the attention weights will decide which encoder output to give more preference, which one to not use that much, which gives us the context vector. Now we are at this stage. We have the context vector. We have the embedding of the previous decoder output. We have the previous hidden state. We concatenate these two and just use the decoder hidden state as the input to our Rnn. So we concatenate the embedding and the context vector. And we use those two, the output of the concatenation and the previous hidden state of the decoder as the input to our Rnn. Apply the log softmax in the end after a classification layer, and that just gives us the output. So its name should be output. So we only added 3 or 4 statements in this, primarily these, and everything actually these. So you apply the fully connected, add things, multiply with another classification layer, calculate the alignment scores, calculate the attention weights, calculate the context vector, and concatenate it. So just by adding these statements, we have modified the decoder network, which we wrote earlier, into and added in the attention mechanism to the decoder network. So then if I wanted to use this decoder network in the sequence to sequence, then I just have to make 2 very, very small changes. This is the exact same thing I wrote earlier. Now, the only change I have to make is, instead of using the final encoder hidden layer, I have to use all the inputs of the encoder. So all the outputs of the encoder, that will be passed to the decoder. So let me just again show this. So yeah, so I have the encoder hidden layer, and I define encoder all hidden because all of the encoder hidden layers are going to be passed to the decoder. I loop over the input length, pass the input to the encoder, pass the hidden layer of the encoder to the encoder, get the new hidden layer, and I keep on saving the hidden layers. So this will be all the encoder hidden layers, which I need. And now, instead of just passing one encoder hidden layer, I'll pass all the encoder hidden layers. So the decoder. So this is another only single statement change I need to make. So the decoder will have an input of the decoder. It will have a hidden layer, and then it will have all the encoder hidden layers as the input. It will return the decoder output. It will return the decoder hidden layer, and it will also return the attention weights. So this is just a small change. So just 2 things are to be changed as compared to the previous encoder decoder we saw. In the previous case, we are only passing the final encoder hidden layer in the decoder. Here we are passing all the encoder hidden layers as an input to the decoder, because in every case, in every step, it is going to use all the encoder hidden layers, and it forms, and using the attention mechanism, decide which layer to, which hidden layer to give more weightage, and which one to give, which hidden state to give more weight, and which hidden state to give less weight. So yeah, and then everything else remains the same. You can define it in the same way. The train model function, which will be there in that notebook I'll share, will just work similarly. So these are the only small changes which you need to do to add the attention mechanism to the normal encoder decoder framework. And then the functions for the training loop and other things I'll share in the other notebook, so you can take a look there.
So yeah, thanks for being here, everyone. We'll see you in 2 weeks. We'll be talking about transformers, and multi-head attention, self-attention, and so on. So this is part 2 of this. We'll see you next week.